Welcome to solverfy.
In this problem, we have light shining through three separate materials, each with a different index of refraction here, labeled N1, N2, and N3. We're given that the indices of refraction are N1 equals 1.55, N2 equals 1.6, and N3 equals 1.33. We're also told that the thickness of the middle layer, labeled L here, is 285 nanometers. We can see from this diagram that there are two possible paths that the light can take in getting through here, and in general these two rays are going to be phase shifted one from the other, which will cause an interference pattern. In this problem, they want us to find what wavelength in the visible spectrum will result in a minimum intensity, so that would be complete destructive interference between these two rays. This means that the extra distance that the ray 4 here has to travel, which is going to be twice this thickness L, must be some multiple of half the wavelength of the light. So twice L, which is the extra distance traveled, must result in a phase shift of half a wavelength. So we can write that as lambda, and it's lambda over the index of refraction because it's the wavelength not in the vacuum, but the wavelength in this material with index of refraction N2 times some integer minus 1/2. Right? So m is 1, 2, 3, etc. And so that this quantity is always going to be some half multiple of the wavelength. There may be another phase shift we have to consider because at the reflection, at the surfaces, sometimes you get a phase shift. So if the index of refraction goes from lower to higher index of refraction, then you get a phase shift on the reflected ray. So at this first reflection here, between N2 and N3, we're going from higher index of refraction to lower index of refraction, so there's no phase shift. And same thing on this surface, where we're going from N2 to N1, we're going from higher to lower. So again, there's no phase shift here, so this equation down here is correct. Now we just have to solve for lambda. We get that lambda is going to equal 2 times N2 times L over m minus 1/2. And m, for each m, there's going to be a different lambda. And so we have to try different m's until we get a wavelength lambda that's in the visible spectrum. And I'll remind you, the visible spectrum, we have wavelengths between 400 to 700 nanometers. So we can try here. First, this numerator here, if we plug in the numbers, is going to be 912 nanometers. And then we're going to divide still by m minus 1/2. So we can try m equals 1. Well, m equals 1 means we're dividing by 1/2, which is going to make the numerator larger, and the numerator is already outside the visible wavelength. So we know this is not going to be a solution, but I'll write it down anyways. For m equals 1, we have that lambda equals 1824 nanometers. So that's not in the visible spectrum, so that's no good. Try m equals 2. Now we have that lambda equals, so m minus 1/2 will be 2 minus 1/2, which is 1.5. So we have 912 divided by 1.5, which works out to 608 nanometers. And that is in the visible spectrum here. And lastly, we'll try m equals 3 to see if that's also in the visible spectrum. And when we plug that in here, so m equals 3 into this equation, we get that the wavelength is 365 nanometers, which is outside the visible spectrum. So the only wavelength and the answer to this problem is lambda of 608 nanometers.